I heard you still program, but how much programming were you doing back then? You mentioned the hours, probably insane hours. So like it'd be almost fun to talk about your setup. What a day in the life of Tim Sweeney in the '90s when you're building Unreal looked like.
Well, we'd all gravitated towards a work schedule that maximized productivity, and that usually meant waking up late. Usually get to work around noon. Usually work till like 2 a.m. or so, 3 a.m. sometimes. And
Nice.
I didn't have anything else going on in my life, so it was really just work and sleep and occasional eating. And uh, I found I always needed 8 or 9 hours of sleep a night. Without good sleep, I would just become a zombie and wouldn't be nearly at my best. So I always needed to get sleep, but I didn't need anything else going on. So the programming itself was so energizing and enthralling. Um, yeah, so it was 3.5 years of that during the project. Mostly spent programming. I'd say probably 60 hours a week of programming, 5 hours a week of coordinating with other people and iterating and sitting down with them and looking at what's going on in screen and figuring out what they needed. Maybe 5 hours of business stuff. There's a good division at labor then. I didn't have a big executive team, but it was like basically myself running the technical and development part of the company, and Mark Rain running the business part of it, doing deals and maxing out his credit card and going around the world bringing in sources of revenue to keep the company funded.
What programming language are we talking about? C? Because you mentioned there's this pile of assembly. Did you what was your decision in choosing the programming language that Unreal Engine would be written in?
I'd grown up learning with Pascal as my favorite language.
Nice.
In order to just get maximum performance and get the latest operating system features, I had to move to C for my second game, Joel of the Jungle, a little Nintendo-style platformer. And so when I started Unreal Engine, it was on 16-bit Windows using the C programming language. And over the course of the first year, it moved to 32-bit, using these DOS extenders and then using Windows NT. And I moved to the C++ language, and just because it simplified the code so much, went from a really complicated pile of code to a much simpler one, making that transition. And so almost the entirety of Unreal Engine development, about 2.5 years of it, was all in C++, 32-bit, completely state of the art then. Like 32-bit protected mode was kind of a magical thing, having come from the days when computers were much less reliable and crashed all the time.
Yeah, and turned out to be a pretty good bet because C++ out of all those languages ended up being the dominant sort of performance-oriented language that survives to this day.
Yeah, it's because it solves all of the problems at scale, often through manual pain, but always solves them. And a
Yeah.
lot of other languages do better in a lot of like theoretical aspects and are better for some usage cases, but you can't do everything, and that's really very limiting.
All right, so ridiculous questions, but like, did you have one monitor, two monitors? Were you picky on the keyboard? Were you
Okay,
picky on the chair? What are we talking about? Let's paint a picture.
okay, I went through a big transition there. So I started
Okay,
out
great.
being pretty lazy. I'd had a bunch of like I bought used computers because you'd often get them at half the price of a new one. They'd be good enough. So I had this old 486 I was developing on. I guess it was a 15-inch monitor at the time. It was a poor workstation setup, but it was very economical. And so as we started on Unreal, I realized that I had to write a ton of code. I had to write it at absolute maximum productivity. So I had to rearrange my entire life around delivering maximum output. And so at that point, I realized like actually spending money on getting good equipment was a good investment. And we're not talking about millions of dollars here, or billions if you're building a GPU farm. We're just talking about buying some basic hardware. And so I bought the biggest CRT you could buy at the time, because this was a CRT era. It was 24 inches. It weighed like 100 pounds. I had back pain for a week after I installed it, but it got me 1920 by 1200 view
Wow,
in
nice. State of the art.
1996. In 1996, that was pretty cool. So I'd upgraded to a 90 megahertz Pentium and did a lot of programming on that. It was on the 90 megahertz Pentium. These were the main consumer computers at the time, and I'd optimized the Unreal Engine software render on that, which was, yeah, the Pentium was the first scalar architecture in consumer computing. It could run up to 2 instructions at a time, and if you wrote your assembly code very carefully, you could get absolute maximum throughput. So I'd gotten my texture mapping code down to 6 CPU cycles comprising 11 instructions. That was required for every pixel on the screen, and that was just enough performance to deliver that. Um, but Dell came out with these new workstations, and Intel had just launched the Pentium Pro, the first out-of-order processor. Um, and so I like basically bought the absolute maximum configuration that money can buy. It cost $7,000. I had a gigabyte of memory in
Nice.
1996, and a 200
Wow.
megahertz CPU. So it like tripled the speed of compiles and just made me massively more productive. So that's why I was using throughout Unreal Engine development and shipped with that.
By the way, people in the 90s would have been blown away by this workstation. I love it. Yeah, yeah. Were you in writing, were you considering the hardware much? Was there a sense like for people who don't know, Unreal Engine rendering, I guess, is all software, it doesn't use the hardware. But were you trying to optimize, as I understand, maybe you can correct me, but like, were you trying to optimize to the hardware at all?
Well, at the time, so we did most Unreal Engine development before the first real GPUs came out. And the 3D Effects Voodoo one, the first GPU that actually delivered serious performance compared to software rendering. The first GPU that was really gainful came in the end of the development, and we supported it really quickly, but it was not the target all along.
Hmm.
And so development was focused on just building. There are two parts of the engine, right? There's all of the gameplay systems that manage the simulation and physics and so on. That's all written in very high level C++ code. And maintainability is as much of a goal as performance, because we had to build massive amounts of systems over time. But there were one thing that was really a bottleneck was graphics. The cost of rendering a single pixel was really high, and so you had to do everything you possibly could to optimize the rendering of pixels on screen. And so we were talking about how many CPU cycles. When you say your CPU runs at a gigahertz or whatever, that's a billion instructions per second. How many instructions do you need to run to get a pixel on screen? And so there was a constant challenge to optimize that down. And there was also a competition among all of the graphics programmers who'd often send emails, like bragging to each other about what new technique they've discovered, to try to get the cost down. And Abrash's original articles took like 12 CPU cycles to render a pixel, and everybody else had figured out how to get it to like down to 6 or sometimes even 4 cycles. And that involved lots of different trade-offs of caching and memory hierarchy and so on. It was just like a magical time where a human could actually understand exactly what the CPU was doing under the hood and could write code that exactly targeted that. Um, and that's largely lost now. When we talk about optimization and software now, it's largely about heuristics and statistically, this memory access is likely to hit the cache. And this algorithm is faster than that algorithm. Because CPUs now have such advanced out-of-order execution that you really can't micromanage what's happening on an instruction by instruction basis. You can only manage the aggregate performance of code. And so there's kind of this lost art. Some people miss it, some people don't, in which the programmer had absolute control over the machine and could work miracles in special cases if you tried.
It seems like there's still value to that art when it comes to GPUs and ASICs. So basically, trying to understand the nuances of the hardware and how to truly, truly optimize it, whether it's for machine learning applications or for ultra realistic real time graphics applications. Is that true?
Yeah, that's absolutely so. The optimization problems have just moved around.
Yeah.
In a system like Nanite, the virtualized micropolygon geometry system that Brian Karras, a brilliant engineer with Epic, built, was just one of those multi-year optimization efforts that required understanding everything from the highest levels to the lowest levels of the hardware to figure out how to make this breakthrough technique work in a way that was actually maximally performant on GPUs.